Golden. Okay, so moving on to the second day of chapter 3, which involves two very important theorems. So there is a, I wouldn't say a rule, but there's an idea in calculus that says if a theorem has its own name, it's important. It's important like you would put a blue box around it in your notes, like you would put it on a note card, like it's something that's going to come up repeatedly. Today we have two of those theorems. One is called Rolle's theorem, and the other one is called the mean value theorem. Again, named theorems, therefore they're important. However, they're both fairly simple, and we're going to take our time and make sure that you understand it before we go on. The concept of the theorems is straightforward. The application can sometimes be tricky, so as long as you understand the foundation, you should be good with the application. Okay, so like I said, Rolle's theorem and the mean value theorem. We're going to talk about Rolle's theorem first. It's crucially important that you understand Rolle's theorem before we move on to the mean value theorem, because the mean value theorem is a variation of Rolle's theorem. Okay? And then, of course, today you should be able to count to 10 in German. Anybody? Nobody? Nicht sehr gut, meinen Schatzis. Was ist los? Bitte meine Tagstunden. Okay, so that was disappointing. Can you count to 10 in any language? Yeah? Ryan, what language?
Spanish.
Any others?
English.
Oh, that's a good one. Good one. That's funny. You got me. Jerk. Okay. So, Rolle's theorem. Before I click on the next slide, I'm going to explain Rolle's theorem all on this cute little slide. And hopefully this will help. All right, so we're going to start with level ground. Okay? And we're going to start at level ground, and we're going to end at level ground. So we'll call this point A, and we'll call this point B. And somewhere between A and B is a hill. Okay? Sitting on this side at point A is a big boulder. Your job is to roll that boulder over the hill and end at B. Okay. Any confusion so far on the setup? We're good? Okay. So here's the concept. If I roll that boulder up the hill and then back down to B, and it's important that they're both at the same level, does it not make sense that at some point in time I'm going to hit the top of the hill? We're all good at that, yes? Okay. Now, it is possible that I could hit a top a couple times. Like, let's say my hill looked like this. Number one, that's not something you'd want to roll a boulder over, but you could hit it. But at least one point, I have to hit the top of the hill, the high point of the hill. It appears that it's here. Okay? Good. Yes? Understand the concept. Okay. Let me review a couple important points. We have to start and stop at the same level. As we roll the ball, or the, boulder up the hill, somewhere along the line I'm going to hit the top of the hill. And then come back down to the ending point at B. Okay. Now, if you understand that, Rolle's theorem should be pretty easy. You'll notice it's called Rolle's theorem. It's named after a French mathematician named Rolles. But we're also talking about rolling a boulder up a hill. So hopefully that will help you remember this. Here's the fancy calculus speak. Okay. Michel Rolle. Okay, let's break down the calculus speak here. First of all, it has to be continuous. Okay. Otherwise, the whole theorem collapses. And it's continuous on the interval from A to B. A is our starting point, B is our ending point, and differentiable on the interval. Well, that doesn't have a lot of relevance here. We're assuming that we can take the derivative. We'll be good to go. Then we get to, on the interval AB, if f of A is equal to f of B. That's a fancy calculus way of saying we're starting and stopping at the same y value. Because remember, our points now are x comma f of x. Then f of c equals 0 at least c in the interval. So there's got to be at least one point where the derivative has a value of 0, which is also known as a horizontal tangent line, which is also known as a maximum, the top of the hill. Now, to make things a little bit more interesting, if you understand the whole hill concept, we could do it again, but instead of doing it instead of doing it over a hill, we could, come on. There we go. We could do it down into a valley. Okay. Here's A, here's B. You roll the boulder. At some point, you're going to hit the bottom of the valley and then have to roll it back up. Okay. And you'll notice in Rolle's theorem, at least C in the interval. Could be more than one, could be a lot, could be an infinite number, but there's got to be at least one point where you hit the top of that hill. So if you think about that from a physical approach, if you don't start and stop at the same value, then it doesn't make any sense. That just means you're rolling a ball up a hill. That's not what we want. We want to be able to start at a level, roll up a hill, and end at the same level. If a function goes from one y value to another equal y value, the slope of the tangent line must equal 0, somewhere along the way. Okay? Give me a thumbs up if you're okay with the concept. Awesome. You crazy kids? We're good? Okay. How do we apply that? Well, it's funny you should ask. Here's a function. I got a parabola. That parabola opens up. So we're not going to deal with a hill here. We're going to deal with a valley. But it doesn't matter. It handles it the same way. And that parabola goes on forever and ever. So therefore, it's restricted to an interval. Now, there's a couple things I don't know. What I don't know is, am I going to start and stop at the same point? So I have to check to see, does f of 1 equal f of 2? And before I write this all out, I think I have this done already, so I can just click through it. Actually, the first thing I need to talk about is, if we go back to the theorem, one of the things I underlined is that it has to be continuous. Is this a continuous function? How do you know, Tessa? And a parabola is a common name for a parrot is what do you commonly name a parrot? What? Huh? What do you commonly name a parrot? Anybody? What do you commonly name a parrot? Polly. So a parabola is also a polynomial, and we know that all polynomials are continuous. Good. That took a while, but we got there. Good job. Okay. So we've satisfied the initial condition, one of the initial conditions. It is a polynomial, therefore it's continuous. Now we need to know, does it start and stop at the same point, same y level? Okay, so what's f of 1? 1 minus 3 is negative 2 plus 2 is 0. Ooh, 0. Put in 2. 2 squared is 4. 4 minus 6 is negative 2 plus 2 is 0. Bingo. We've satisfied what we call the hypothesis of the theorem, also known as the first half of the theorem. Okay. This does nothing for us except make sure that we can apply Rolle's theorem. The rest we've done already. Take the derivative, 2x minus 3, and set it equal to 0. This is the same thing as the c value that we were talking about right there. Quick question. Other than the calculus, how else did I know that that was going to be the answer? What's significant about x being equal to 3/2 in this particular problem?
The vertex.
Beautiful. It's the vertex of the parabola. So we've got a parabola facing up like this. We picked a point 1, 2, and it's going to be the bottom of that parabola. So instead of going over a hill, we're actually going down into a valley. It's the low point of the valley.
Sir,
Yo.
isn't the vertex negative b over 2a?
Mm-hmm.
Negative. Oh my god. Okay. Yeah, sorry.
I'll let you get there on your own.
Yeah.
Good. Okay. Good? Questions? All right. Like I said before, it's important that you understand Rolle's theorem before we move on. So if you have any questions whatsoever about Rolle's theorem, ask now. All right. Beautiful. Here we go. Now, if we modify Rolle's theorem, we get the mean value theorem. And how are we going to modify mean value theorem from Rolle's theorem? We're going to change the starting and stopping points. We don't have to start and stop at the same point for the mean value theorem. Okay. Okay, still the same rules. It's got to be continuous. It's got to be differentiable. What we don't care about is starting and stopping at the same points. They can be all over the place. Okay, so f is continuous and differentiable on the interval from a to b. There exists a c in a to b such that, wha-bam! That is a train wreck. That jumped pretty quick. That's crazy. What's going on? I'm confused. It's simpler than you think. Okay, and it'll make more sense when I show you a picture and work you through an example. But the thing you want to remember with mean value theorem is the slope from calculus is equal to the slope from algebra. So write that down.
So the slope from calculus is equal to the slope from algebra?
That's the heavy metal answer to yes. Yeah. Okay. Could have given you the thumbs up, but I went with the heavy metal. Okay. I thought you'd be with me there. You're good? All right,
Yeah.
good. Notice I didn't give you the double. It wasn't that exciting. It's just a single.
Yeah, column.
Right, right. Okay. Confused, yes? Yes, yes, yes? Good. Okay, that's fine. That's okay. Let's go back to this picture, because I can. This guy. Woo! Okay. Now, notice, this is confusing. Let's make that go away. Let's go back to our original picture that we're rolling a ball up a hill. Because we're starting and stopping at the same level, that guarantees that this thing, the ground, is level. And by being level, it has a slope of 0. Then, when I get to the top of the hill, we've already learned that that would become an extrema. It would also have a slope of 0. So the only difference between mean value theorem and Rolle's is that in Rolle's theorem, it has to be 0. The slope has to be 0 each time. Okay, level ground, top of the hill or bottom of the valley, always 0. Mean value theorem, however, takes that restriction of 0 out of it and just says they have to be equal. Okay. This is the slope from calculus. This is the slope from algebra. Again, sorry, I'm jumping around like crazy here, but okay. This is the slope from algebra. Okay, calculate the slope between the point A and the point B. This is the slope from calculus. Take the derivative, set it equal to 0. Hopefully this is starting to sink in a little bit, so let's keep going. Most of the time, this first part is going to be your preferred way of looking at the mean value theorem. However, this also appears a little bit, and that's just multiplying by b minus a. All right. How does this work? Okay. So, there's a picture. So I took a parabola, and I picked 2 points. I picked the point A, and I picked the point B. And again, this is calculus, so the point A is going to be at A, comma, f of A. The point B is going to be B, comma, f of B. And I can calculate the slope of this line. Okay? y2 minus y1 over x2 minus x1. Oh, yeah! That's the slope from algebra. Also known as the slope of the secant line. Slope of secant line. This other line in red is the slope of the tangent line. You'll notice it hits the point of tangency right there, and it only touches the graph once. Let me ask you a fairly obvious question. How do the slopes of these 2 lines compare?
They're the same.
Which makes these lines what from geometry?
Parallel.
Parallel, correct. Okay, so hopefully the picture helps a little bit. Are we good so far? Everybody caught up?
Mr. Reed.
Yo!
So the difference between Rolle's theorem and the mean value theorem is that Rolle's theorem has to be on, like you have to start and end at the same level, and then mean value.
The slope is 0. Okay, mean value theorem, we could turn it around or tilt it. All right, here we go. Mean value theorem. Another parabola, a little crazier parabola, still opens up, similar to the picture I probably had in the previous slide. And all I'm going to do is I'm going to apply the little mantra that we had, the slope from calculus equals the slope from algebra. This one I think I can click through. Oh, yes, I can. All right. That function, we've discussed this already. Tessa helped us with this earlier. It's a parabola. Parabolas are polynomials. Polynomials are continuous and differentiable. We're good to go. But you must check that every time. By checking it, I mean, if this is on the AP test, you need to specifically say, this function is continuous and differentiable because it is a polynomial. And you're good to go. Okay. So, 2 columns. Let's do algebra first. We have an interval from 2 to 7. Those represent my 2 x values. I need to find the y values. How do I find the y values? Well, remember, x comma f of x. So plug 2 in, plug 7 in. That's over here. You'll have to trust my math, or if you'd like to get out your calculators, you can plug and chug. Then under the calculus column, I went and took the derivative, because that's not rocket science. I can do that also. Do a little bit more algebra and calculate the slope of the secant line, which would give me 15. For those of you that are visual learners, I know you're trying to write, I'm sorry. For those of you that are visual learners, that 15 represents the slope of this line right here. And now I got to find the point where this line would also have a slope of 15. Okay. How do I do that? Just like I did it with Rolle's theorem. Take the derivative and set that puppy equal to 15, because the slope from calculus equals the slope from algebra. Slope from calculus is 10x minus 30. The slope from algebra is 15. Set them equal and solve. And that happens at 4.5. In this case, only one situation. It is possible to have more than one situation.
So the slope you get from algebra is the secant line slope?
You got it. Yep. Questions? How can we make it more interesting? Oh, there's a lot of ways. Well, first of all, we could throw some trig in there. Yeah, I'm not going to do that to you. Not today. Not on the day before Halloween, even though I hate Halloween.
Why?
I always have since I was a kid. I don't know why. It was probably something that happened when I was a kid and I just forgot about it, scarred for life type thing. You know, maybe I was in therapy as a kid and somebody helped me work through it and I just forgot about it. My parents have never told me, but I've always hated Halloween. Like, I literally have the sign hanging outside my door, like, don't come here for Halloween, it's COVID, stay away. I was either going to do that or I was going to put candy all over the front yard, like 6 feet apart, and then just let people come in. But I know some jerk could come by and just break the lawn and take all of my Snickers bars, right?
For sure.
Yeah. So, how did we get off on that tangent?
Because you said you don't want to do that to us the day before.
Oh, yeah, day before Halloween. Right, so, okay, so, what was I saying? Sorry, I got derailed by Halloween. Making it more interesting. Okay, so let's do this guy. 5 minus 4 over x. That's not a continuous function, right? X cannot be equal to 0. It's asymptotic. That's a fancy word. However, this happens very frequently. The interval that's been chosen for this problem goes from 1 to 4. This function is continuous from 1 to 4. Yep. So we can apply mean value theorem. The entire function doesn't have to be continuous, just on the interval. Does that make sense? Yes? Good. Solve this problem. Find C. This will be fun. Sarah, everything okay? Okay, good talk.
Yeah, well, my mom is like tweaking and she thinks there's like a gas leak at my house, so she made us go to my grandma's house.
That's probably a good move.
She said she heard a weird noise or something.
All right.
She came into mine.
I got to be honest. I've seen a lot of things in my years of teaching. I would not like to see one of my students blown up on Zoom. So going to grandma's house was probably a good move on your part.
Yeah.
Okay.
Is this video gonna be like on Schoology later?
Do you not want it on Schoology? You want to air your dirty laundry on Schoology? Or do you want to show it to your mom and say, look,
I wanted to see so I could like catch up on what I just.
Oh, it has nothing to do with the gas leak. I see what you're saying. Okay, I thought you were worried about the gas leak information being on Schoology. You just want to get caught up now that you're in a safe environment.
Yeah.
Yes, sure. I'll put it online and I'll leave the gas leak discussion in there so you can share it with your friends and family.
All right.
All right. This was a good talk, sir. I'm gonna go back to work.
Okay.
Okay. Bye bye. Any progress for the rest of you?
Is C equals 2?
I don't know. What's C equal? Anybody? Anybody? 2? Well, let's see what I got. What's f of 4?
1. Yeah. Or 4, sorry. 4.
Yeah, f of 4 is 4. What's f of 1? 1, strangely enough, yeah. So we get 4 minus 1 over 4 minus 1. Last time I checked, that's equal to 1. Okay. Gavin, you got the derivative for me?
I got it as negative 4 over x squared.
Close.
Yeah.
4 over x squared.
Okay.
Because notice we already got a minus sign, so we'll bring the negative 1. Okay, so then 4 over x squared is equal to uno. That's Spanish for 1. Or ein in German, but we know that nobody can help me there. So x is equal to plus or minus 2. Uh-oh.
Would it just be positive 2?
Just be 2. Why?
Because it's not, negative 2 is in MVT.
Good. 2 is the only answer because negative 2 is not in our original interval. Hot diggity. I think I got all this. Yeah, I did that. Good. 1. Yep. Good. Yeah. Oh, plus or minus 2. Oh, perfect. You guys are smart fellers. Done. Now, let me explain the picture. That is a bridge. I think it's in South Korea, but somebody thought it would be a great idea to put the mean value theorem across a bridge. And I know what you're thinking. You're thinking, why can't we have bridges like that in America? And I don't know. I ask that question on a regular basis.